Good morning. So today we shall see the Norton's theorem. Earlier we have studied the Thevenin's theorem, and according to the Thevenin's theorem, we have seen that any complicated two-terminal linear complicated network can be replaced by a simple series circuit consisting of a constant voltage source in series with an equivalent resistance called as Thevenin resistance. So, with the help of Thevenin's theorem, we can analyze the given network in terms of its voltages. But in accordance with the Norton's theorem, we can analyze the given network in terms of its currents. In terms of the currents, we can analyze the given network. So, in accordance with the Norton's theorem, any complicated network, two-terminal complicated network consisting of sources of EMFs, resistors and so on can be replaced by an equivalent circuit consisting of a constant current source called as Norton current source in parallel with an equivalent resistance called as Norton resistance. The value of this Norton current source IN is nothing but the short circuit current that will flow across the terminals A and B, and the equivalent resistance or Norton resistance RN is nothing but the equivalent resistance of the given network when viewed backwards from the open terminals A and B when all the sources of EMFs have been killed for their EMF. When all the sources of EMFs have been short circuited. All the sources of EMFs have been short circuited for their EMF. So, when we have such a situation, so in accordance with the Norton theorem, any complicated network can be replaced by a parallel circuit consisting of a Norton current source IN in parallel with Norton resistance RN. So that is how we can use this Norton theorem in order to analyze the given complicated network in terms of the circuits. So this Norton equivalent circuit, this is the Norton equivalent circuit for the given complicated network. This Norton equivalent circuit consists of an ideal current source, ideal constant current source IN in parallel with an equivalent resistance called as Norton resistance. So we can state the Norton's theorem like this: any two-terminal linear network, containing the source of EMF and resistances can be replaced by an equivalent circuit consisting of a constant current source IN in parallel with an equivalent resistance called Norton resistance. The value of this constant current source is nothing but the short circuit current that will flow through these terminals A and B. When we put a short across the terminals A and B, whatever the current that will flow through this short circuited terminals A and B, that is nothing but the value of IN. And RN is nothing but the equivalent resistance of the given network when the sources of EMFs have been short circuited, when the network is flowed backwards from the open terminals A and B. And if all the sources of EMFs are short circuited, then the equivalent resistance of this network will give us the value of I. So that is the statement of this Norton's theorem. Now let us prove this Norton's theorem. So to prove this Norton's theorem, let us consider we have a complicated network consisting of a source of EMF E in series with the resistances R1 and R2 connected across the terminals A and B, and across the terminals A and B, a load resistance RL is connected. This will be load resistance RL, this will be resistance R2, this is the resistance R1, and this is the source of E. And we have this complicated network. To the left of the terminals A and B, and to the right of the terminals A and B, we have the load resistance RL connected. Now, when we want to apply this Norton's theorem in order to obtain the Norton's equivalent circuit for this complicated network, what we want to do, we want to first prove this Norton's theorem. So, the proof, we can say that the Norton's theorem is verified if and only if, let us consider the Norton equivalent circuit like this. This is the constant current source IN in a parallel with Norton resistance RN. To the left of the terminals A and B, and to the right of the terminals A and B, we have this load resistance R. This is RN, this is I. So, when can we say that the Norton's theorem is verified? In case if the current flowing to this load resistance, if the current flowing to this load resistance or the potential drop across this load resistance is same, in case if there is the given complicated network connected to the left of the terminals A and B, as well as if the potential difference across this load resistance RL is same as even if the given complicated network is replaced by this Norton equivalent circuit. So, irrespective of whether there is the given complicated network connected to the left of the terminals A and B, or that complicated network is replaced by this Norton equivalent circuit, the potential drop across the load resistance RL, if it remains same in both these situations, then we can say that the Norton's theorem is verified. So, let us try to obtain the potential difference across this load resistance RL when there is the given complicated network connected to the left of the terminals A and B, and this complicated network, if is replaced by this Norton equivalent circuit, and this Norton equivalent circuit is connected to the left of the terminals A and B. Again, in this situation, if we obtain the potential difference across this load resistance RL, and in both these situations, if we observe that the expression for this potential difference across the load resistance remains same, we can say that the Norton's theorem is verified. So, let us first obtain the expression for the potential difference across this load resistance RL when there is the given complicated network connected to the left of the terminals A and B. So, this can be obtained. To obtain the potential difference across this load resistance, first we must know the current IL flowing to this load resistance RL, and by using the Ohm's law, then we can obtain the potential difference across the terminals A and B or across this load resistance RL. Now, for that purpose, what we should do is we should know the total current I sent by this battery. If this current I arrives at the junction, a certain part of the current will flow through R2 and a certain current IL flow through RL, so that since R2 and RL are connected in parallel, the potential drop across R2 and potential drop across RL are equal. So by equating these potential drops, then we obtain the expression for IL. So before obtaining the expression for IL, first we have to find out the value of I, the total current drawn from the source. So to find the total current I drawn from the source, we must first know what is the total resistance of the circuit. The total resistance of the circuit is R1 plus R2 parallel R. The total resistance of the circuit is R1 plus R2 parallel R. So total resistance of the circuit is equal to R1 plus R2 parallel RL is nothing but R2 RL upon R2 plus RL. The equivalent resistance of the parallel combination of R2 and RL is R2 RL upon R2 plus RL. So this is how we get the total resistance of this circuit. Now once we get this total resistance of the circuit, we can find out the potential difference across R1 and Rx. In this situation, let Rx is the Rx. Let us consider this is Rx. So the total resistance of the circuit is R1 plus Rx. So the total current I drawn from the source is E upon R1 plus Rx. So this is equal to E upon R1 plus R2 RL upon R2 plus R. This is the total current I drawn from the source. This is the total current I drawn from the source. Now, once we know this total current I drawn from the source, now since here in this situation R2 and RL are connected in parallel, so we can say that PT across R2 is same as the potential drop across RL. The potential drop across R2 and potential drop across RL are equal because the two are connected in parallel. Now, if I is the total current drawn from the source, part IL flow through load resistance, so that the current flowing through R2 will be I minus IL. So the potential drop across R2 will be R2 into bracket I minus IL, and this will be equal to IL I. So if we open up this bracket, it can be written as R2I minus R2 IL is equal to IL. And if we transfer this term to the right hand side and take common, so this is I into R2 is equal to IL into bracket IL into bracket R2 plus R. Therefore, IL is equal to what? R2 upon R2 plus RL into I. IL will be equal to R2 upon R2 plus RL into I. And using this expression for I here, we get IL to be equal to R2 upon R2 plus RL into I. I is E divided by R1 plus R2 upon R2 plus R. So, taking LCM here, we can explain this as E R2 divided by R2 plus R into 1 bracket for iron. So this R2 plus iron, this R2 plus iron is going to cancel. So we have the expression for iron. That iron is equal to ER2 if we open up this bracket, it can be expressed as R1 plus R1 plus R2 or if we club these two terms, this can be expressed as ER2 divided by R1 plus R1 plus R2 and dividing both numerator and denominator by R1 plus R2. This can be expressed as ER2 by R1 plus R2 divided by R1 R2 upon R1 plus R2 plus R2. So this is the expression for current IL knowing this load resistance R. And knowing the current with this load resistance R, now we can obtain the potential drop across this load resistance R. The potential drop across the terminals A and B will be equal to the product of IL and I. The product of IL and I gives us the potential drop across this load resistance R. So this VAB is nothing but equal to VAB is nothing but equal to using this expression for IL here, we can write VAB is equal to ER2 upon R1 plus R2 into R divided by R1 R2 upon R1 plus R2 plus R. So this is IL into R, that gives VA. So this is the potential drop across the load resistance RL when we have the given complicated network connected to the left of the terminals A and B. So we shall write this expression for VAB here. VAB is equal to ER2 upon R1 plus R2 into R divided by R1 R2 R1 plus R2 plus R. This is when we have the given complicated network connected to the left of the terminals A and B. Now, if this complicated network is replaced by the Norton equivalent circuit, what will be the potential drop across this resistance RL? That is what we want to calculate. Sorry. This is RL. This is so this is I. So we want to obtain the Norton equivalent circuit for this, and then the RN and to the right of the interface in the B of the load resistance I. This is I. So we want to obtain this Norton equivalent circuit for the given complicated network. So for that purpose we have to obtain the values of IN and RN. This IN is nothing but the short circuit current that will flow through this flow through this short circuit put across the terminals E and B. So what we need to do is, from the given network, if we put a short across the terminals A and B, the network we get will be of this type. So we have this source of here and E, the resistance R1, the resistance R2, and if we have these terminals A and B here, this is R1, this is R2, this is E. So if a short is put across the terminals A and B, this resistance R2 gets short circuited. The resistance R2 gets short circuited so that the current I flowing through this short circuit ISC is nothing but the total current I drawn from the source, because this resistance R2 gets short circuited, and if this resistance R2 gets short circuited, whatever the current is drawn from the source, all that current will flow through this short circuit. So this short circuit current ISC will be equal to E upon R1. ISC will be equal to E upon R. And this is nothing but the value of I, the Norton, the constant current source I. So we have obtained the value of I. So once we obtain the value of I, now we want to obtain the value of I. To obtain the value of I, what we need to do is, we have to remove this short circuit from the terminals A and B, and this source of EMF is short circuit. So if the source of EMF is short circuited like this, what will be the value of equivalent resistance when this network is viewed backwards from the open terminals A and B? That is the value of R equivalent, and this R equivalent is equal to R. So when we view this network backwards from the open terminals A and B, it appears that R equivalent is nothing but the parallel combination, equivalent resistance of the parallel combination of R1 and R2. So this is nothing but equal to R1 R2 upon R1 plus R2, and this gives the value of R. This equivalent resistance, when viewed backwards from the open terminals A and B, gives us the value of Norton resistance R. So once we know the values of IN and RN, now we can calculate the value of IN flowing through this load resistance R. Let IN is the current flowing through this load resistance. So if IN is the current sent by the source, certain fraction of the current will flow through RN and certain current will flow through the load resistance R. So if we use the current division formula, the current flowing through this load resistance R will be given by this expression. IN is equal to RN upon RN plus RN into I, the total IN into IN. So that is the total current in the circuit. So using the expressions for RN and IN here, we get the expression for IN. Using these expressions for RN and IN here, we get IN is equal to RN is R1 R2 upon R1 plus R2 divided by RN plus RN. RN is again R1 R2 upon R1 plus R2 into is IN, and IN is E by R. So this R1 and this R1 will get cancelled. So what are the left over terms? The left over terms here are ER2. So IN is equal to ER2 by R2 plus R2 divided by R1 upon R1 plus R2 use this I. So we have this expression for I. The current going to the load resistance RL when there is the Norton equivalent circuit connected to the left of the terminals A and B. So once we know the current IL flowing to this load resistance RL, therefore the potential drop across the terminals A and B, that is across the load resistance, is nothing but equal to the product of IL and R. So using this expression for IL here, we get the expression for the potential drop across the load resistance RL when there is a given there is a Norton equivalent circuit connected to the left of the terminals A and B. So VAB is equal to, using this expression for IL here, we get ER2 by R1 plus R2 divided by R1 R2 R1 plus R2 plus R1 into I. So this is the expression for the potential difference across this load resistance when there is the given when there is Norton equivalent circuit connected to the left of the terminals A and B. So here we have obtained the expression for the potential drop across RL when there is the given complicated network connected to the left of the terminals A and B. This expression for VAB and this expression for VAB when there is the Norton equivalent circuit connected to the left of the terminals A and B appears to be same. So both these expressions for VAB are same. So what we can say is that we can say that the Norton's theorem is verified. So or else we can just compare the expressions for IL also. In case when there was the given complicated network connected to the left of the terminals A and B, and that complicated network when is replaced by this Norton equivalent circuit, we get the same expression for IL, the current flowing through load resistance. Either we can compare the currents flowing through the load resistance, or we can compare the potential drops across this load resistance in the two different situations. In the first situation, when there is the given complicated network connected to the left of the terminals A and B, and when that complicated network is replaced by this Norton equivalent circuit, again if we get the same potential difference across this load resistance, in both these situations we can say that the Norton theorem is verified. So for this video we'll close it here, and next we shall see how to normalize the given network. Okay. Thank you.